On 2023, December 2nd, I made a theory the two different infinities uncountable, which is the amount of decimal numbers between 0 and 1, and countable, which is just the amount of whole numbers, are actually the same infinity. I thought that because decimals and whole numbers are basically the same kind of thing, you can match up 1 with 0.1, 2 with 0.2, and then eventually you can matching up 1736 with 0.1736, and it's a one-to-one assignment, so it's the same infinity. But is it really? Because then I thought, yeah, you can go on forever with both of them. But the thing is, for just the whole numbers, you can keep getting bigger and bigger whole numbers forever, but there's no actual number with an infinite number of digits. The only infinity in the whole numbers is that it goes on forever and ever, but there is no actual infinitely many digits whole number. Because listing whole numbers, it's a one-way trick. That's why you can list them. That's why it's a countable infinity. There's no number you won't catch. But if we look at decimals, the decimal of 1/9, for example, goes on forever. And it doesn't just limit out like 0.1, 0.11, 0.111. Those exist as well, of course, but no matter what listing method you use for the decimals, some decimals will always be missed out, and that's actually going to be the majority, or even 100% of the decimals, like these random decimals that just go on forever, like pi. They follow not much of a pattern. Basically, almost all of the decimals are going to be missed out, because there will always be gaps in every listing process, and you're trying to list a continuous range, because they do not fit. Unlike the whole numbers where they just all fit, nothing's missed out. It's like you can get 111, 111, but you can't actually get a number with ones going on forever. You can't get an infinitely big number in the whole numbers, because then you just say that's infinity, and despite there being a quote-unquote infinite number of whole numbers, every one of those numbers is finite, right? You can't have an infinitely big number. But the thing is, with decimals, you can have infinitely big numbers, or rather infinitely long. And I was thinking that you could just match up every integer with a decimal and there would be none left over, because basically take every positive integer and put it in front of a decimal point and turn it into a decimal like that. But then I realized that despite it going on forever and theoretically listing all decimals, in every step of the way I'm listing a terminating decimal that stops at some point. But the reality is, if you just randomly were to pick a number between 0 and 1, it's pretty obvious to see that the chances of that decimal somehow stopping at a point, and mind you, that means it having 0 every single decimal place after that, infinitely long, by complete random chance, is basically no chance at all, actually. The chance is 0 if you randomly pick a decimal and it's terminating. Which made me realize that actually, compared to what's out there in terms of the decimals that just go on forever and stuff, the amount that this lists is nothing. So in terms of the infinity that's just like the natural numbers, the positive whole numbers, it's basically 0 compared to the infinity of decimals between 0 and 1. And that's because decimals, even between 0 and 1, are a continuous range. There aren't like discrete values like for the whole numbers or even the rational numbers. They're all listable, those ones, but this is a continuous range. You can get more and more precise with smaller and smaller increments, but you can never get as precise as continuity like the decimals are. And when I talk about decimals, it kind of makes it feel like discrete and individual, and it feels like it's just approximating it, but really it's not just a decimal, it's the actual value. It just can't be represented fully with a decimal. It's a continuous range, so that's the difference. And there is an actual number with ones going on forever. And this kind of infinity, I feel, is not really just the infinity of approaching a limit, but infinity as an actual number. So you're actually at the limit, you actually get there. About limits, actually, when we approach a limit as x tends to 0, it's easy, we can just go down to 0. But when x approaches infinity, we just keep going forever, like 1, 2, 3, 4, and so on. But we never actually get there. In the case of 1 divided by x, as x approaches infinity, it does actually tend to something, obviously 0. So it seems like it's not just a limit, but an actual number that it's tending to. It's not just getting bigger and bigger forever, which is what infinity means. It feels like it's tending to an actual number. A number that, if put through the function, will give you the number that it otherwise just seems to approach but never get to, but it will actually give you that. That is anti-zero, which I mentioned in my previous videos. And I feel it's the limit of infinity, because as x gets closer and closer to 0, 1 divided by x goes to infinity, but when it's actually 1 divided by 0, then it's anti-zero is what I said. So I know it's the limit that way. I made it up, but it's basically infinity as a number. It's 1 divided by 0. A great example of this is when I thought, what is 1 divided by infinity? Because infinity, at least I thought at the time, was the biggest possible number, and I was kind of confused between the infinity of numbers getting bigger and bigger with no end and infinity as an actual number, which it turns out are two completely different things. So I just kind of merged it together and thought of this idea of infinity as the biggest possible number, but still acting like a finite number. Like 1 divided by even infinity, it acts like a finite number, so it couldn't be 0, but the smallest number greater than 0. But actually, I kind of mixed the two up into something that didn't really exist, and I clarify that later. But it turned out that the idea was completely preposterous, because there can't be a smallest number, but it's greater than 0, because there's always going to be a number between two different numbers, so you can't really have the smallest one. And it really seemed like 1 divided by infinity was just 0, but I thought, how was that possible? It turned out I was mixing the two infinities up. But then I realized what I was trying to think of was the actual limit of 1 divided by x as x goes to infinity, but not what it would be at like the biggest number and it would act like a number. What it would actually be at the limit. Instead of just it tending to 0, the answer, that when we say at infinity, 1 divided by x is 0, we mean like infinity as an actual number. We're treating it like a number here, not one of the finite numbers you would get from approaching something, like not as going on forever. So countable infinity, you can list it like it goes on forever and ever, and you can list it like that. Like if you use like a listing method, like 1, 2, 3, 4, 5, 6, 7, 8, and that's the positive whole numbers. But for an uncountable set like the decimals, you could use a listing method like 0.1, 0.2, 0.3, 0.4, and so on. But using that listing method, that set includes not only the numbers listed with the listing method while it approaches more and more long stuff, while it's approaching something, trying to list them all, but it also includes those very numbers that it is trying to get to, like the numbers with infinite decimal places, for example, just an example. And it actually includes those as well that are actually at the limit. It includes those which have an infinite number or anti-zero decimal places. And you can't list an uncountable infinity like the decimals, because if you try, you're only going to get discrete values in every step of the way. No matter how many decimals you list, you're never going to get a continuous range. You're only going to get discrete values, because there are an infinite number of different decimals in that continuous range, and not just the infinity of that they go on forever. They have an actual infinite number of decimals, and you actually have to get to infinity or anti-zero, which is just impossible if you just count up regularly and in the number of steps. You have to have anti-zero steps of whatever listing method you want to list all the decimals, and you can never get there, and you only get closer and closer to there as you count up like 1, 2, 3, 4 steps of the listing method, but you can't get there because it's a different type of number. It's not in the whole numbers. It just gets closer, but only closer. However, with the decimals and something like does 0.33333333 really equal 1/3? In the limit at anti-zero decimal places, it does, but of course you can't get there in just the finite context, and I was mixing the two infinities up. That's how the differences link together. There are two different types of infinities, one as a number where it's actually there, and one where it's not actually there, it's just getting bigger forever. An even better example of this, I think, is the question is 0.999999 going on forever equal to 1 or not? I always thought of it like, in every step of the way, if you have 0.99999 any amount of times, you can always add another 9, or you get a number between that and 1, so you can't actually get to 1. And there's always a 0 in front of it, so it's never at 1. And that is right, at any number of 9s you put, no matter how many 9s you put, it will never get to 1, because there's always going to be that one little bit of space left between it and 1, no matter how small it gets. But the thing is that if there are anti-zero 9s, then it equals 1. That doesn't really make sense at first, but if you think about it, it does approach 1. And if you think about it at infinity as a number, there's no last one. It's complete. Counting up to that number, you can never get there by just going in 1, 2, 3, 4, 5. But if you shift your perspective a little bit and then think that there is a number out there that represents not just the infinity of getting bigger of finite numbers, but the infinity of actually being there.